Okay, so if you are insulated, and then in this case, work done on the system, that means you compress it. If you got a negative sign there, it means you compress it. Then it must increase the internal energy.
Of course.
Whereas in this case, it tells you there's a decrease in internal energy. Why?
Decrease in
Because
energy.
work done by the gas, it expands. Conservation energy. Okay with that?
Yeah, so 0 equivalent to internal energy plus W, you switch here, switch there, then you get all those last.
You must be able to interpret, see what you want. When solid or liquid is heated, is the expansion significant? Yeah. Is it significant?
Oh, you're asking me. Okay, when solid or liquid is heated, is the expansion is significant? For solid, no. For liquid, yes.
Both of them insignificant, very small only. So usually we won't bother to calculate the work done.
Oh.
Right? So small change in length, same thing. Expand a little bit only. Small molecular movement expansion, that's all. So no work done, negligible. That's why we won't bother about solid liquid. Only gas, the expansion is significant. That's why we have to calculate the work done. Okay?
Okay.
So when we use the first law of thermodynamics on solid or liquid, then the heat supply goes to the internal energy only, no work done. Okay? Thermal energy means heat energy. That's why when you
wait, so what's that? FL.
Okay, now that's why when you study your STPM about heating solid or liquid, we don't bother about telling you work done. Because when you heat it, you supply heat, it goes to the internal energy only, increase the temperature, that's all. Okay, now? Okay, now?
The term, wait, so if the W, the work done is 0, so then it will be internal energy equivalent to the Q.
Yeah, that means where you heat the solid, energy, the heat goes to increase the internal energy, that's all. Okay.
Yeah, the internal energy increases lah. So
any comment? Are you all right?
But how come A is not? Why is it not significant?
Too small, too small. We won't bother. Very, very small.
But what if it's very big?
Then, like gas, we have to consider. That's why we study gas. Very significant. We have to calculate the work done.
All right.
Right? Heating at constant volume. We can show it in a diagram there. Pressure, volume graph. The blue line is called the isotherm. That means it's constant temperature line curve. Right? Obey Boyle's law at temperature T1 and T2. T2 is at higher temperature. So if we use a simple case at constant pressure, no change in volume, then no work done. Right? In this case, no change in volume, no work done. While the pressure increases, we can show in the diagram. Right? No work done. But you heat it up, the temperature increases, the pressure increases. That's your Chow's law. Okay.
Okay, the graph part only I don't understand. Why T2 more than T1? The graph look like that?
PV graph. PV graph.
Yeah, PV graph.
PV equals to nRT. Greater temperature, greater the curve is higher.
Okay.
Right? It's in topic 9. Topic 9, page 209. Right? We are just using PV equals to nRT, that's all.
All right.
What happened to the thermal energy? Right? We use the first law, that's the equation. Right? No work done. So in this case, our Q equals to delta U. And remember, our delta U, our Q is given as N C mv delta theta. Right? Remember this one, our definition for constant volume, heated at constant volume. So it means that in this case, that's how we calculate our internal energy. N times C mv delta theta. They call it delta theta or delta T, doesn't matter. Right? So in this case, we can understand why the temperature increased, because heat is supplied. And then the internal energy increases, shown by the temperature rise. Okay.
That equation you did right, the equivalent part, that part I don't get it.
This part without the delta U is just your definition for molar volume times number of mole times the change in temperature. And then we are just using the first law, delta W equals to 0. So it means Q
So
is
they're trying to tell if they don't have, yeah?
Okay or not? We defined it earlier.
No, sir, repeat again.
We defined it here earlier. If you refer to your note, your book there, right? We defined earlier. This is for constant pressure. This is for constant volume. That's all. And now we are just applying it there. That's all. First law tell us delta Q equals to delta U. So that's why we are using. Okay. So when it comes to constant volume, the heat flows go to increase the internal energy. That's all. So that's how we calculate our change in internal energy. And then molar heat capacity at constant volume times the change in temperature. I have to memorize the formula to use it. Yep. What's the problem?
No, okay.
Okay, then we carry on. Molar heat capacity at constant volume.
So that means the thermal energy increases, right?
Okay now. So the energy that is supplied goes to in the change in your internal energy. Then from our previous topic, we have got our internal energy for ideal gas equals to F divided by 2 nRT. Right? So if there's an increase in temperature, remember our F is constant, our N is constant, our R is constant. If there's a change in temperature, it goes to a change in volume. That's all. That's all. Or differentiate is the same thing. The others are constant. Then at constant volume, we have already shown just now. Right? Delta U equals to Q equals to N molar heat capacity at constant volume times the change in temperature. So we just compare these two, right? Delta T and delta T. So this must be your F and R equals to your CMV. Right? Or we can rewrite that. Right? Take our C MV, take our N delta T down across, then replace that delta U, replace inside here. Right? So we got F, right? This one. And then this is N delta T. N delta T can cancel, so we get R, R, F. Okay or not okay? Cancel the N, cancel the R, cancel the delta T. We got your half RT. Yep. That's the problem. That's the problem. Your book derive it differently. It's okay. Just different people will do it differently.
Yeah, I think I got it.
Okay. Right? Of course, we usually have to relate our theory to experiment. So this diagram basically tell you that how your CV changes with temperature. Right? First, at certain temperature, rotation will be occurring only. After that, after a certain temperature, vibration mode will come in. Right? This is just extra info. That's all. You don't need to go that deep there. Okay, work done in expansion. This is for constant pressure. Right? We look at constant pressure, apply the first law. Same. Work done. Okay or not? Shaded area.
Okay.
This is the work done. Change in volume is V2 minus V1. V1 is the final. Sorry. V1 is the initial volume. What am I doing? V2 is the final volume. Sorry. V2 is the final volume. Let me just remove this one. It may get a bit confusing. Just work done is just a shaded area. That's all. As shown in the diagram there. That is for constant pressure. Okay with me? Okay, let's carry on. Expand from volume 1 to volume 2. Volume 1 is the initial volume, volume 2 is the final volume. So the change in volume is V2 minus V1. Right? Or if you want to write a formula down, that's all. You want the formula? That's the formula that we have derived for you earlier. Either use the shaded area or P times delta V. This is for constant volume. Okay or not? Can we go to the next part?
Yeah, okay.
Okay. So this is another picture just to show you what is happening. Right? If we draw in terms of PV graph, this is at temperature. This one is at higher
T1,
temperature. So it
T2.
means that if it is going to expand at constant volume, it must go to a higher, from a low temperature to a higher temperature. That's all. Right? So N mole of
And the
gas.
pressure is constant.
So N mole of gas in a container as it expands at constant pressure. Right? We are just using the first law of thermodynamics. Q is delta U plus delta W. And in this case, remember, we are looking at constant pressure. So Q can be represented by that. And CMP and delta T. And delta U, we have already said, is N CMV delta T. And then work done is just your pressure times change in volume. Okay. So now we want to replace that delta P delta V. Right? We want to return to delta T. So we can use our ideal gas equation. PV is nRT. Let it change. Remember, our number of mole is constant. Our pressure is constant. So if there's a change in volume, there's a change in temperature. We can rewrite the equation. Right? There's a change in temperature equal to a change in volume. That's all. So P delta V, we replace with nRT. That's all. Then we can cancel our N. Right? Number of mole. And cancel our delta T. And then we get a new equation. You have to memorize this equation. Molar heat capacity at constant pressure equals to molar heat capacity at constant volume plus your gas constant. Molar gas constant.
It's so we cut here and there, lah. That means.
Just cancel the common factor, that's all. Yep. Are you all right? Are you with me? We are now on.
Oh, yeah. PV equals to nRT, right? So teacher just substituted
We are now in
nRT.
247, page 247 in your book.
Yeah. Okay.
You want to replace that P delta V, that's all, with nRT delta T, that's all.
Okay, sir. Okay.
Right? So let's go for the molar heat capacity at constant pressure. Right? Replace just now we derived that equation.
1/2 RF.
F put into the equation plus R. Right? Usually there's a lot of equation. You just memorize this equation for CMV, and then CMP, you just memorize the equation and then derive it. Right? If you prefer to memorize it, go ahead. Half R into F plus 2. If you want to memorize it, go ahead. But as I said, this is too many equations to memorize. Some of it is
It takes very hard time to understand, right, sir?
Okay.
Yeah, okay. That's all.
Okay, that's a topic 9. Right? Internal energy of ideal gas. Internal energy is the total kinetic energy for N molecules is F divided by 2 times nRT. Now I'll just review with you. So increase in temperature of the gas means an increase in total kinetic energy of the gas thus the increase in internal energy. I think better, maybe we should stop here already, or we want to carry on.
I think stop here, lah, teacher.
Since you are so saturated already. Okay, Monday I see you at 3 to 5. Don't want to change anymore.
Okay, teacher.
I give you a
All
topic
right.
topic quiz 2. Okay.
So next week, chapter 2.
Monday
Okay.
3 to 5. Topic quiz 2. Topic 2. Give you a quiz. You can try that out first.
So next week, Monday, you'll give me chapter 2 topic quiz.
Yep. We are doing very well for topic 1. So hopefully topic 2 you can do as well.
Okay.
Okay, I'll stop here.
Okay, see you, teacher. Thank you.
Okay.